바이오 그다음 바이오 프로세스가 업무가 여러 가지 바이오
Okay, let's get started. Just don't forget you all have the Achieve Due Monday. That's really all for now. We're going to finish chapter 18 today. So I will have another PowerPoint posted over the weekend. I'll post an announcement when that's available. Just make sure you have that ready for class Monday. That will be the last PowerPoint. So we'll have a little bit of 19 and probably a little bit of 20. I'll be making that decision this weekend. So continuing with chapter 18, towards the end of class, we were learning about these standard molar entropies. Remember that entropy is a measurement of the number of possible microstates. That's the best definition for what entropy is. It's often described as a measurement of the degree of disorder. Those go hand in hand. If you're increasing disorder of a system, that means that system has greater number of possible microstates. Remember I used that example of kids running around? You take different snapshots. There's a lot of different possibilities of where those kids can be. Imagine particles in place of kids. So gas, lots of disorder, lots of different possible microstates. Liquid particles are more confined and there are fewer possible locations that those particles can exist. For example, there's a bunch of other things that increase entropy. I won't review that again here. We can calculate entropy using standard molar entropy. So these are known values you would have provided in a table, and you can find the change in entropy of a reaction. We'll also call this a system in our notes today. And that is just by multiplying the coefficient for products and their standard molar entropies, subtracting the sum of that of the reactants. So we did these two learning checks actually using that equation, and then now we're going to talk about temperature and how that might influence entropy. So we have delta S of the universe, delta S of a system or reaction, and delta S of surroundings. So remember that for ice melting, the system is the ice, so that's the thing that's going through a change. So ice is melting, that's a phase change. If we have a reaction, that would be the system. Surroundings is the air around the ice, or if you have something in the beaker, it could be the surface of the beaker. The universe is the sum of those two, the system and the surroundings. So the delta S of the universe is equal to change in entropy of the system plus change in entropy of the surroundings. So this is a key equation. We will use this to solve some problems. So I want to make sure you have that written down. Delta S of the universe, so the sum of delta S of the system and delta S of the surroundings, that must be positive. This is the second law of thermodynamics, which says the entropy of the universe is always increasing. So if you have any change in entropy of a system, if you add that with its surroundings, it's always positive. So that can be achieved if both the system and the surroundings have a positive change in entropy. Or if you have a system that's decreasing in entropy, like water forming ice, a liquid becoming solid, that system is decreasing in entropy. That's a negative delta S of the system. That is offset by a larger positive change in delta S of the surroundings. We'll see an example of that. And delta S of the surroundings could be negative, but is offset by a larger positive change in delta S of the system. Key is that delta S of surroundings should always be positive if you're calculating a negative delta S, or sorry, not surroundings, of the universe. If you calculate a negative delta S of the universe, you may have had an error in your calculation. Now we know how to calculate delta S of the system. To calculate delta S of surroundings, well, we'll talk about that on this slide. And then if we can calculate both, we can calculate delta S of the universe. So I'm just going to write, we know how to calculate this. This was section 18.2, the previous section we talked about calculating delta S of a system, which if we say delta S of a reaction, the reaction is the system, so that's the same thing. Now in chemistry, the reaction or the system that we're studying is usually very small compared to its surroundings. So I have this candle on the slide here. Imagine if I had a candle in the room. That flame is a result of a chemical reaction releasing energy. The surroundings is the air around the candle. We're thinking about temperature. Are we going to feel a temperature change in the room by one candle? No, probably not. That system is much, much smaller than the surrounding. So that's an example, but in general, when we're doing experiments, when we're conducting reactions or there's a phase change, the surroundings, temperature change, we're going to assume is zero. It's usually very, very small, and so we'll assume it's zero. Temperature change, we're also thinking enthalpy change, so change in energy. We're going to say the change in enthalpy of the system has a minimal effect on the temperature of the surroundings. So the word for this type of process is an isothermal process. And that just means there's no temperature change in the surroundings. This helps to simplify our delta S surroundings calculations. So then we're going to say that the delta S of surroundings is related only to the thermal energy change of the system. And this all leads up to the equation that we have on the next slide, which is an equation to calculate delta S of the surroundings. So that's what we have here. Now notice it's dependent, delta S of the surroundings is dependent on the energy change of the system, delta H of the system, enthalpy change, divided by the temperature that it occurs. So delta H of the system, or delta H of reaction, we have this equation from Gen Chem 1. It's the same thing as delta H or delta S of the reaction. We're just working with delta H values. So we take the sum of the coefficients of the standard values of the products minus that of the reactants. So the entropy change, delta S of the surroundings, is inversely proportional to the temperature. The effect of energy change on the system, or of the system, on the entropy of the surroundings is smaller at high temperatures than at lower temperatures. So if we have a higher temperature, delta S of the surroundings will be smaller than if we have a low temperature. If we have a low temperature, delta S will be larger. Okay, so we're going to go to our first learning check. Calculating delta S of the universe for a reaction. And then you've got this data table with a bunch of different values here. We need to think about how to use what's provided to answer this question. So remember that delta S of the universe, this is what you're calculating, is delta S of the system plus delta S of the surroundings. So you need to calculate both delta S of the system and delta S of the surroundings. Delta S of the system, we calculated in 18.2. Delta S of the surroundings, you have the equation on the previous slide. I'll give you all like 3 minutes to get started, and then we'll go through it together. So 11, 12. we'll go through it together. But try to at least get the questions started. Let me know if you're unsure where to start. You can start wherever. When I go through it, I will start with delta S of the system, but it doesn't matter where you start. All right, we'll get started talking through it together. So delta S of the system, delta S of reaction, same thing. I've got the equation up there. So we start with the coefficient of the product. We have one product here with coefficient of 1. So 1 mole of silicon tetrachloride. The standard entropy value there is 239.7. So 1 mole times 239.7 joules per mole times Kelvin. Units are important. For each of these, though, I'm going to write out the units for the first part of it, and then I'll leave units out just for space. But seeing the units here, we have moles times joule per mole times Kelvin. This means our final unit should be joules per Kelvin. We're canceling out moles. So that's our only product, and then we do the same thing for reactant. So 1 mole of silicon times its standard molar entropy, 18.8. And then add 2 moles of chlorine times its standard molar entropy, 223.1. This value here is negative 225 joules per Kelvin. Let's think about that value. So we have a negative change in entropy here. Remember, a negative change in entropy means that entropy decreases. That means we have fewer microstates, less disorder in the system. If we look at reactants and products, we have solid and gas forming a liquid. We're decreasing in the number of gas particles in that reaction. Going from solid to gas to just a liquid, that decreases the entropy, the number of microstates. So it makes sense that our delta S is negative. So we've got delta S of the system. Now we need delta S of the surroundings. Looking back real quick, delta S of the surroundings, we need negative delta H of the system and then divide by temperature. So let's calculate delta H of the system first. This is, I'm not going to write out the equation, essentially the same thing as delta S, but instead of standard molar entropy, we have standard molar enthalpy, H values. Writing out units for the first one, again, we have 1 mole. Now, these molar entropies are in units of kilojoules per mole. We've calculated first joules per Kelvin, and then we're going to have kilojoules, so we'll need to do a conversion. So be careful with units. You don't want that to be a reason you don't get an answer right on the exam. Write out their units, please, when you do these questions. So enthalpy for silicon tetrachloride, negative 687.0. And then for reactants, these are standard states. So 1 mole times silicon, standard molar entropy, which is 0. And then 1 mole or 2 moles times chlorine, standard molar entropy, which is, or enthalpy, sorry, which is also 0. So delta H of the system is negative 687.0 kilojoules. Now we can use delta S of the surroundings equation. Negative delta H of the system divided by temperature. Delta H we just calculated. And then temperature provided as 298 Kelvin. This is 2.31 kilojoules per Kelvin. Okay, turn to someone next to you and tell them what to do next. How do we finish this problem? All right, will someone tell me what to do? Yes, Amira, go ahead.
We're going to take the kilojoules and make them into joules.
Why do we have to convert kilojoules to joules?
Because we're dealing with, if it was the enthalpy, then we would have changed the delta S into kilojoules, but we're not going to do that.
Okay, why do we have to do a conversion at all? We need to make sure the units are the same. Yeah, we're about to add this energy, this amount of energy, and that amount of energy. One's in, or sorry, up there. One's in kilojoules per Kelvin, the other one's in joules per Kelvin. So we need to do a conversion. You could convert joules to kilojoules and add them together if you're doing a multiple choice question and your options are in kilojoules. But we're converting kilojoules to joules. Okay, so let's do that first. 1,000 joules for every 1 kilojoule. Okay, so delta S of the surroundings, is 2,310 joules per Kelvin. What's next? Someone else? It's very simple, I think. Yeah. Plug it into what? Yeah, to the equation at the top. We're just going to add these values together. So using delta S of the universe equals delta S of the system plus delta S of the surroundings. We're trying to calculate delta S of the universe, so we just need to add these together. Again, that's why we converted kilojoules to joules, so we could add them. So negative 225 joules per Kelvin plus 2,310 joules per Kelvin, 2,080 joules per Kelvin is our final answer, delta S of the universe. Now notice that although entropy of the system decreased, the delta H of the system was large number and a positive number, delta S of the surrounding, was a large positive number, so that the delta S of the universe is still positive, and that follows our law of thermodynamics. Okay, questions on this problem here? All right, let's continue. Chapter 18, we'll start talking about Gibbs free energy. This combines enthalpy and entropy and temperature into one equation, and Gibbs free energy is used to predict if a process, if a system, if a reaction or a phase change is spontaneous under the given conditions. So notice that T, this is temperature, is part of the calculation. A change in temperature can determine if certain reactions are spontaneous or not. H is enthalpy, and S is entropy. So no new components except for G, which is Gibbs free energy. So if we're talking about the change in Gibbs free energy for a process, we take this equation here and put deltas in front of everything that would change. We are assuming constant temperature and pressure. So the change in Gibbs free energy of a process is equal to the change in enthalpy of that process minus the temperature times the change in entropy. Then if that change is occurring under standard conditions, standard temperature and pressure, then we put that degree symbol in front of each of those, the G, the H, and the S. So delta G at standard conditions is equal to delta H at standard conditions minus temperature times delta S at standard conditions. So this allows us now to use known values. We have standard molar entropies, standard molar enthalpies, and then we can then calculate the change in Gibbs free energy. So we're going to do that. So let's do this learning check here. You're determining delta G for the reaction of hydrogen and oxygen forming water. You have delta H, you have delta S, just simply plugging it into the equation that was given to you. And I also think Gibbs free energy equations on your equation sheet. We're assuming standard temperature 298 Kelvin here. Now I have to be careful with our units here. Delta H values, usually if they're provided to you, they're in kilojoule units. Delta S values are usually in joules. So again, be careful with your units. Let's convert joules to kilojoules. Okay, so the delta G for this reaction at standard conditions is negative 457.1 kilojoules. We've canceled out temperature units, Kelvin. We're multiplying by Kelvin there. So just kilojoules for our units. Okay, so I mentioned that delta G can be used to determine if a process is spontaneous or not. This is all summarized on the next slide. A decrease in Gibbs free energy. So if the delta G is less than 0, the ending Gibbs free energy is less than the beginning Gibbs free energy. This corresponds to a spontaneous process. Which would mean it is spontaneous in the forward direction. And then the opposite is true. An increase in Gibbs free energy, so delta G is greater than 0 for a process, indicates a non-spontaneous process. In the forward direction, but it would be spontaneous in the reverse reaction or reversed direction. And then if you ever calculate delta G equal to 0, the system will be at equilibrium. Neither forward or reverse direction is favored. And then just to fill in the table, it just summarizes what's on the slide. So delta G is less than 0, spontaneous. At equilibrium. Non-spontaneous for delta G greater than 0. It kind of sounds like K, but it's a little bit different. For a reversible reaction, if a system's at equilibrium, let's add K over here. K would be, or if a system exists in equilibrium, neither side is favored. K will be equal to 1. If the forward reaction is spontaneous or the forward reaction is favored, K is greater than 1. If reverse reaction is favored, K is less than 1. Just wanted to add that in, but we're really focusing on G in this chapter. So question on the next slide. Is the reaction of hydrogen gas and oxygen gas to form water vapor spontaneous? So that is the learning check, but we had already calculated delta G for this reaction on the previous slide. Delta G is negative 457. Spontaneous or not spontaneous? What'd you say? Spontaneous, thank you. Yes, we're just looking to see if it's negative or positive. Negative value, spontaneous. Now there's another way to calculate delta G. We have standard molar entropies. We have standard molar enthalpies. There are also standard molar Gibbs free energy. This is the energy change, the free energy change in the formation of a substance from its elements in their standard states. So for an element in its standard state, the delta G is 0. An example of this is nitrogen gas, N2. That is the elemental form of nitrogen that's found in its elemental state on Earth. It doesn't require any energy for that to form. It doesn't release any energy. It just is. So delta G for an element in its standard state is 0. Delta G for something else like H2O. We just looked at O2 plus H2 forming H2O. That had a delta G value. That's because H2O is the combination of elements from their standard states, H2 and O2. So H2O has a standard Gibbs free energy, a standard delta G. And so we can use the same setup to calculate change in Gibbs free energy for a reaction using standard delta G's of formation of products and reactants. So it's another way to calculate delta G. We can use delta H minus T delta S, or you can use this if you have the provided values. So let's do that. Let's follow the same pattern as the rest of the notes here. So given all of these delta G formation values, calculate the change in Gibbs free energy for this combustion reaction, combustion of propane. I'll write that delta G equation here, but again, all right, so let's take coefficients of product. I'll start with carbon dioxide. We have 3 moles carbon dioxide times its delta G of formation, negative 394.4 kilojoules per mole. So our final units will be kilojoules. I'll leave out units for the rest. Then we have 4 times delta G of water, negative 237.1. And that's all the products. And then subtracting reactants, they're both 0. For delta G. Oh no, they're not both 0. 1 times negative 23.4. 0 just for oxygen. All right. So the result of the first set of brackets is negative 2,131.6 kilojoules. Second set of brackets is negative 23.4. Final value here is negative 2,108.2 kilojoules. So the combustion of propane, delta G, negative 2,108.2 kilojoules. Spontaneous or not spontaneous? Spontaneous. Do you know what propane is used for? You all used it? Your backyard, maybe? What's it used for? For grill. Yeah, for a grill. I'm sure it has plenty of other uses, but that's what comes to mind for me first. Is propane tanks are used to supply the gas for a grill. Okay, so this section, we've got delta G at standard temperatures. Our last section, delta G with changing temperature. It's a very short section here. So for this delta G calculation, remember that negative delta G, ingrain this in your memory, negative delta G is spontaneous. So with the equation that we have here, so we have a process, the process has some delta H value and some delta S value. For different processes, those values can be positive or negative. So if you have a process that has a negative delta H, releasing energy is what that means, a positive delta S, increasing entropy, then you have a negative delta H, and then negative T delta S will end up being negative as well. And delta G will be negative at any temperature. It doesn't matter if you have a high temperature, low temperature, you'll always get a negative delta S. Now if you have the opposite sign, so you have a positive delta H and a negative delta S, then when you subtract T minus delta S, subtracting a negative number, you're actually adding it. Adding that to the positive, delta G will always be positive. This is a process that requires energy to occur and decreases in entropy. So this is unfavorable given that systems favorable systems increase entropy and release energy. So that will be non-spontaneous at any temperature. Then if we have both negative or both positive, it depends on if we have a low temperature or a high temperature, if that reaction is spontaneous or not. So temperature will affect if a reaction is spontaneous, if it has negative delta H and negative delta S, or positive delta H, positive delta S. So let's think conceptually about this. Negative delta H, so that's good. We want to make sure that when we subtract T delta S, that is not a largely positive number. So if it's negative, we're subtracting a negative, that means we're adding. So if that value is small, meaning we have a low temperature, then overall delta G will be negative. So these reactions are spontaneous at low temperatures to get a negative delta G, not spontaneous at high temperatures. Then if we have both positive, delta H is positive, so we need to make sure that when we subtract T times delta S, that's a largely negative number. So if T temperature is high, then it will be spontaneous. If temperature is low, it's not spontaneous. So certain reactions depend on the temperature if it is spontaneous or not. So let's end with this example. We have a reaction, a phase change, titanium fluoride liquid to gas. It has a positive delta S and a positive delta H. Liquid to gas requires energy, it's endothermic, and it increases entropy, so we have positive delta S. So you're calculating delta G using delta S and delta H at two different temperatures. You want to see at room temperature, is that reaction spontaneous? And then at a high temperature, is that reaction spontaneous? I've set up the first one, delta H, 41.0 kilojoules, temperature, going with 298 K for the first calculation. Delta S, 100.9 joules. We need energy units to be the same, so I converted joules to kilojoules. Delta G here is 10.9 kilojoules per mole. So this is not spontaneous at room temperature. But at high temperatures, we're going to get the second half of the equation. Although it's positive, we're going to be subtracting a really large number. And as you can probably predict, that will result in a negative delta G. And then this value here is negative 37.2 kilojoules per mole. So we have an endothermic reaction with a positive delta H. That means energy is required for that reaction to occur. And so if it has sufficient energy surrounding that reaction, like a high temperature, then it will occur spontaneously. But without that extra energy in the surroundings, it won't occur. Yeah.
Why aren't the units just in kilojoules? Why is it kilojoule per mole?
Yeah, so I should have had kilojoule per mole here, Kelvin times mole. That's what they're provided is in the table. And that's because this delta S, for example, is the change in entropy for 1 mole of titanium chloride. And that's just how we calculate that in a standard way, to have it per mole. Other questions here? Okay. We are doing review for the end of class. We finished chapter 18. Woohoo. Let me start the quiz. So the first question is to balance an equation. So you have I think it's a combustion reaction if I remember correctly. All right, so if you need we did a very fast switch there. So I'll leave this open for a little bit, but balancing the number of each atom type on the right and left. Yeah, so how many were you saying? And you have the same on the other side? So, yeah. Okay, did everyone submit? All good? All right, I'll end it here. No, not everyone? Okay, so when you're balancing equations, the best way to go about it is to look for atoms that are only present in one molecule on the left and one molecule on the right first. So do not start with balancing oxygen because it's in two molecules on the right, and that's going to complicate things. You could start with carbon or hydrogen. Carbon, we have one on the left, one on the right, so we're good. Hydrogen, 4 on the left, 2 on the right. That means we need a coefficient of 2 here. Oops. And then looking back at oxygen now, we have a total of 4 oxygen atoms on the right and only 2 on the left, so we need a 2 there. So our coefficients, now we can double check everything is balanced. 1, 2, 1, 2. What's that there? I have another one, but we don't have time for it, so we'll do that on Monday. Keep a lookout for the PowerPoint. Hey. No, just 2 things. Yes.
You mentioned that there'd be some stuff in there. Is it going to be like half and half, or is it going to be?
No, it is about half and half.
Okay, is it going to cover like what kind of stuff is it going to cover? I'm curious.
It does cover like something from each of the chapters. I can't tell you exactly what's on it, but
Okay.
I think it's useful, and like we've done some review for different chapters, and then I think it's useful to go back. I'm gonna open all the adaptive quizzes from Gen Chem 1 chapters, not for extra credit, but just for like extra practice if you want to like go refresh. And then we should have at least 1 full class, maybe 2, just dedicated to review, and we can go through like different topics from each chapter.
Okay.
Yeah.
All right.
I know it can sound overwhelming now, but hopefully when you review Gen Chem 1, it won't be so bad.
Okay. Me too.
Yeah. Yeah, you too.
Teaching Orgo.
I just teach it off term.